Okay, so I wanted to go over what we went over in class today. Some of you guys weren't here, and I forgot to record it while we were all in here in the classroom. I got a little busy, got caught up with stuff, but I want to take some time to go over what we went over in class that's new, and you may have not seen it yet, and you just weren't here today, or you just needed a quick reminder, okay? So let me make my pen font a bit larger. So one of the first things that we went over in class today, we kind of went over the things we already talked about, such as impulse, momentum, elastic collisions, inelastic collisions, and those formulas that went with it that you can see on the video that I uploaded from yesterday. But today, we started talking about those angular motions again. So we've talked about angular velocity, angular displacement. We have talked about centripetal acceleration, which is just like angular velocity and stuff. And now we are talking about angular momentum, okay? We've talked about linear momentum, okay? And now we are going to talk about angular momentum. So this is the momentum of an object that is either experiencing rotational motion or circular, okay? It applies to both. Okay, it applies to both these types of motions that we have seen or discussed or looked at. So let's just go ahead and just draw a circle. Okay, let's draw a circle and kind of get an idea going of what is taking place here. I'm going to add a couple of arrows so we can see its direction. And this can be anything. Okay, just put an arrow so we know the direction here. Okay, so we have a formula with it, but what we need to understand with angular momentum is that it behaves very similarly to linear momentum in that it is conserved, okay, and it can be transferred as well, okay? So our angular momentum is represented by a capital L, okay? And its formula, okay, its formula is the mass, okay, times its angular velocity, and I'll make sure to put the angular velocity formula up here too, so we can kind of remind ourselves what that is. Angular velocity, then finally multiplied by its radius in meters, okay? Its radius in meters. All right, so let's say we have this object, maybe we say like a moon, or a comet, or something orbiting a planet, okay? And I'm going to use a really small planet's orbit, something like Pluto, something smaller than that, okay? So let's say the mass of this moon, rock, comet, okay, is 5,000 kilograms equals the mass. Okay. And let's say that we've already kind of calculated its angular velocity on the circular path to be, let's say angular velocity, to be, let's say, just for the sake of the example, let's say it's 15 meters per second. When things are in circular motion, we can also say radians per second, which is a change in degree, a change in an angle. We're going to just keep it simple and say 15 meters per second for now. And the radius, okay, the radius equals, okay, let's say that the radius is going to be around, trying to say something that's kind of realistic too. Let's just say for the sake of the example. It's 500 kilometers. Okay? Sorry, y'all. I'm also in a virtual class at the same time while trying to do this. So I have my AirPods in listening to a class that I'm in and trying to go over this with you. Okay. So we have 500 kilometers as a radius, 50 meters per second as that angular velocity, and 5,000 kilograms for the mass of that object. So again, we have to be in meters, so we have to convert our kilometers. Okay, so just kind of go over that again. Okay, so that's going to be 500,000 meters. Okay, so we're going to plug that in. That would be 5,000 multiplied by 15 multiplied by 500,000. Okay? And obviously when we do this, it's going to be a large number. Let me go ahead and calculate that. Sorry, I'm having to do two things at once. Okay. All right, so this gives us a relatively large number, and that would make sense for the angular momentum to be extremely large in celestial bodies, okay? So the overall angular momentum that I got was 3.75 times 10 to the 10th power. And that 10 to the 10th power is just saying that this 10 to the 10th power says this decimal point would move 10 places to the right. So, it's more like 3 trillion, it would be like around 3 trillion, whatever our unit of measurement for momentum would be for angular momentum, okay? So pretty simple. Basically, we just find the mass, our angular velocity, and the radius, calculate that to create our angular momentum, okay? Okay, so we also didn't just talk about angular momentum, we talked about this thing called angular inertia, okay? Angular inertia, which we use capital I to symbolize it, okay? And the way in which we find that is we take angular momentum and we divide it by the angular velocity, okay? So in that specific scenario, with what we worked on in the first one, okay, and we found that our angular momentum, okay, was 3.75 times 10 to the 10th power, okay? And then our angular velocity was 15 meters per second, okay? So we would divide those two numbers, okay? So I can just divide on the answer that I just got. Okay, divide by 15, and, okay, again, another large number. Our angular inertia is 2.5 times 10 to the 8th power. 1, 2, 3. Ooh, my bad. It's actually 10 to the 9th power. Sorry, people are talking to this online class. I'm trying to do this at the same time. Okay, anyways, angular inertia. So I'm going to do a quick demonstration to kind of give you an idea of what angular inertia is. We used a couple of things in class today to kind of show what that would look like. And so I have a bicycle, like on a spoke here, kind of works like a gyroscope, okay? Kind of works like a gyroscope. When I spin it this way, okay, we see it's going this way. When I turn it this way, I can feel a resistance to that change in motion, okay? So, and then think about it. When things are constantly spinning, okay, that kind of falls into Newton's first law of inertia. Things want to resist a change in motion, okay? They're wanting to change, they're wanting to resist that change of motion, okay? And when things are in an angular motion, rotational or circular, they want to resist that change. Okay, so this thing will spin and spin and spin for a pretty long time. Gravity's eventually going to cause it to stop. But if we were in a plane or universe that was frictionless and lacked gravity, this thing would continue to spin and 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 spin without stopping. And this is why our Earth is able to rotate on its axis without coming to a stop. Okay? It's leaning and rotating on this axis and spinning. Okay? And without gravity, okay, the pull of gravity from the sun isn't enough to stop it from rotating on its axis, but it is enough to hold it into its circular orbit, which is a good thing, because if we didn't have that circular pull, we would fly off into space and Earth would probably run into something, get really cold, and we would all die. We wouldn't have the light that we needed to live, or we'd fall into a star, and that just wouldn't be any fun. Okay, so angular momentum, angular inertia, it's not a huge aspect of this class, but with this being a more advanced section, we definitely want to understand circular and rotational motion all the way through. Not just what it is and what it looks like, but how it feels and how it works as well. Okay? Okay, so the only other thing that we really talked about in class today was mechanical energy. So let me pull up another page. Okay? Mechanical energy, okay? And so mechanical energy deals with all of those things that have mass or in motion, or not in motion, okay? Anything that has mass that is found in our universe is going to have a type of mechanical energy. And there are three of those, okay? We have three of these. We have kinetic, we have kinetic energy, potential energy, okay, and thermal energy. Okay? Okay, kinetic energy. So kinetic energy deals with those things that are in motion. So objects in motion, actively moving, things that are changing position, have velocity, are experiencing kinetic energy. That is the energy output of something in motion. Okay? Vice versa, potential energy is kind of like its opposite. Okay? So potential energy is the stored energy found in objects that are stationary, or stored energy in objects at rest. Okay? And then thermal energy. So thermal energy, okay, is the form of energy, it's the output of energy, output/conversion of energy into heat. Okay? And all of these have a formula, and we will be working with all of them. And we will primarily be working with things in a linear direction or a linear motion. That could be falling, moving on a horizontal axis, or falling in a vertical frame, that sort of thing. But our formula for kinetic energy is 1/2 multiplied by the mass, okay, multiplied by velocity squared. Okay? Stored energy in objects at rest. Okay? This is potential energy. Its formula is really easy. It's mass times 9.8, that acceleration of gravity plays a huge role in how much potential energy an object is going to have stored within it, multiplied by its height. Okay? So, we have kinetic energy, which its primary thing that affects it is how fast it's moving, how quickly it's changing position, which is velocity. Okay? Then we have potential energy, and potential energy, I guess you could say that the most important aspect of this is how high it is, how tall the height, and height is measured in meters. Okay? So the height of an object is going to be the one that dictates how much potential energy is going to be stored up into the object, and concurrently, how much kinetic energy can be produced from that potential energy. And we'll talk about like total energy and the conservation of energy as well. Okay? Now, thermal energy is slightly different. I have to double check what I'm writing because I don't want to tell you anything wrong. But thermal energy deals with something called a heat, or a heat of capacity, a specific heat capacity. That's what it is. Okay? So, to calculate thermal energy, and we'll do just a little bit of this, this more so falls under the laws of thermodynamics, but I still want us to go ahead and get introduced to this topic, have a basic understanding of what it is. Okay? So we have the mass, again, of an object, multiplied by its specific heat capacity, which everything that has mass has the ability to produce heat, and we represent that with C. Okay? And then we multiply by the change in temperature, or delta capital T. Delta meaning the difference, okay? These are our three primary forms of mechanical energy. And think about it. Something that is storing up your energy, like your car when it's parked, right? You turn it on, you put it into drive, and you go into kinetic, okay? And as you were experiencing kinetic energy, those tires have a lot of surface area against concrete, right? Going very fast at times. And if you've ever got out of your car and kind of walked near your tire or brushed against your tire or touched a tire, you know it gets really, really hot, okay? It gets really, really hot. And kinetic energy will typically lead to thermal energy, and thermal energy is due to friction. So friction always causes objects to do what while they're in motion? To slow down, okay? So it's almost like one will be converted into the other. So potential energy typically leads to kinetic, and kinetic typically leads to thermal, okay? And we have a couple of simulations that we can look at to see that. Okay, so I'm going to pull it up. There it goes. Okay, I'm just going to show you part of this simulation. We'll work with some other things. We'll actually calculate the kinetic and potential energy of objects in real time. Okay, so we have a bar graph here, and we have like a skateboarder. I'm going to move this up closer just so you can see it a bit better. Oh gosh, sorry y'all. Okay, so we have kinetic, potential, thermal, and this thing called total. So the total energy is the potential, kinetic, and thermal energies added up together within a system. Because you can be experiencing all three of these at once, and they are never going to be more than the total energy. Okay, so they add up to be our total energy. Okay, and so one thing you're going to notice as I lift this skateboarder up, okay, the higher I lift this skateboarder up, the higher the potential, and thus the higher the total. Okay, so I'm going to let her go about right here. And one thing you're going to see is this back and forth motion in between kinetic and potential. They are constantly going up and down, okay? And so potential energy is highest when she's at her peak, and lowest when she's at this little crevice, okay? And kinetic energy is the exact opposite. It's the lowest at her peak and the highest at the little crevice, okay? So potential energy and kinetic energy have an inverse relationship, meaning that if I have lots of kinetic energy, I typically have lower amounts of potential energy. If I have high amounts of potential energy, I have low amounts of kinetic energy and vice versa. Okay? So they have inverse relationships. So this one doesn't really have any friction in it. So let's look what happens when we add friction. Okay, we're going to put that bar graph up there again. We see that our potential is dictated primarily from the height of our skateboarder, but we're going to put it right here. Okay? And as you see, as we're going back and forth on this ramp, every little run increases our thermal energy, right? The faster we are moving, the more contact we have with another surface, we are going to increase that friction, that exposure to friction, and thus with more friction, more heat is generated, okay? And we typically lose energy to heat in a lot of different ways, not just in like skateboarding, okay? And if you look over here, our total energy and thermal energies are the same, okay? So this is also talking about the conservation of energy. So the conservation of energy states that we cannot create nor destroy energy, but we can convert it into a different form of energy, okay? Like car wrecks, we lose a lot of in car wrecks we lose a lot of energy to thermal energy, to heat energy. It converts kinetic energy into thermal energy quite quickly. We can also lose energy to sound energy. So like when you clap your hands, some of the energy that your hands are, I guess, like experiencing, that kinetic energy within your hand is going to be lost to sound, okay? So sound necessarily isn't a mechanical energy. It's kind of like a product of other like combination of energies. But one of the biggest things you need to understand is that kinetic and potential have an inverse relationship, so they are opposite of one another. Thermal energy is generated due to friction, right? Two surfaces rubbing against each other, and we lose a lot of kinetic energy to thermal energy, okay? One other thing, all of these energies, okay, kinetic, potential, and thermal, they are measured in something we call joules, Joules. So when we were to find our answer, we put like 25 capital J to represent 25 joules of energy, okay? So those are the things that we went over in class today. We had a little bit of fun. We did a couple of demonstrations with toppers and the bicycle wheel. We are going to be moving into the simulation. Once we get through mechanical energies, we're going to have our next test, okay? We're going to talk about two other things before we take that test, which include work and power. So just because next week's homecoming does not mean we can take a stop and do absolutely nothing. That cannot happen. And I hate that we can't take a week-long break, but that just simply cannot happen. We cannot fall behind. We cannot forget what we have covered. And we have to constantly remind ourselves what we have already learned and how it applies to what we are now learning. Okay? So I'm going to go ahead and stop this video now. I'm going to upload it to YouTube. I make links for these videos that I attach to Schoology. So hopefully you got something from this. And if not, again, I'm more than welcome to work with you like after school or in a different block. Awesome.